In this presentation, we'll go through a final set of applications of the first law of thermodynamics. Adiabatic processes, we'll talk about non-ideal gases, and calorimetry, the nice application of the first law of thermodynamics to chemical systems. So those are sort of our goals. Let's get started. Okay, so starting with our fourth key gas process. Here is our cylinder of argon, initially at 400 Kelvin and 0.2 liters. It's at that 1 bar of pressure initially, and we compress it quickly so that there is no time for heat to flow to or from the surroundings until we reach V is equal to 150 milliliters. So this final volume here, 150 milliliters or 0.15 liters. We're going to compress. So yeah, we want to think about what's going to happen during that process. You can take a minute to try to predict the signs for each of these on your own, and then I'll go through and answer those with you. Okay, so predicting the signs, always a good thing to do when you're doing these problems. It's easy to make mistakes, but if you sort of think logically through what's happening, you should be able to get the signs correctly. So first, there's no time for heat to flow. So that's Q is equal to 0. Adiabatic, just like adiabatic walls, an adiabatic process is one in which there's no flow of energy as heat. Okay, the work, what are we doing? We're compressing it. So again, if we think about it, we don't really know what's going on in this diagram yet, but definitely we have that change in volume from 0.2 liters to 0.15 liters. That's compression. Anytime we compress our gas, maybe this is the final state down here. Anytime we compress, we're doing work on our gas, increasing its energy, so work has to be positive. Since Q plus W is delta U is positive. Okay, some other ones here. Delta P, we're compressing the gas, that's increasing its, that's decreasing its volume, and again, we're assuming ideal gas law behavior, so PV equals nRT. So the reduction in volume is going to cause an increase in pressure, all else being equal. I guess we should check what the change in temperature is first. For the change in temperature, we remember that for a monoatomic ideal gas, we have U is equal to 3/2 nRT, and so delta U is 3/2 nR delta T. And so since we know that U increases, then T has to increase as well. For delta P here, now, again, let's be careful with what's going on here, but we have the pressure decreasing and the temperature increasing. Maybe it's useful to solve this for P and use this form of the ideal gas law, nRT over P. During this process, we know temperature is increasing, volume is decreasing. Both of those factors are going to lead pressure to increase. Okay, so from that just analysis of the signs, we can get some idea of what's going on in this process. What should happen here, right? We're increasing temperature and we're decreasing volume. Remember that we always have sort of that adiabatic line here, which is that 1 over X type behavior. That's a constant 400 Kelvin. The temperature is increasing. Higher temperature lines are at further out, right? So maybe 500 Kelvin is out here. I don't know what the final temperature yet is. We haven't calculated that, but right. We have to go from the 400 Kelvin isotherm to some new higher isotherm. So it's got to be something maybe like that, where we're increasing the temperature, which we can see by the fact that we're moving off that 400 Kelvin adiabatic, 400 Kelvin isothermal line, going to some new higher temperature here. Maybe up here is the final state. Okay, so just like the other ones here, now we need to start applying the first law of thermodynamics. In this case, we're going to start from the differential form. So du is equal to d bar q plus d bar w. And again, there's no non-mechanical work, so this is du is d bar q plus d bar q plus d bar work mechanical. dq, again, by definition for this process is 0. no time for heat to flow from the surroundings, so we just have the change in energy is determined by the mechanical work. So that's nice, and the mechanical work, again, is going to be, can plug in du is equal to d bar q, work mechanical, using the definition as negative p external dv. Now, since we're assuming this process is done reversibly, we can now say that p external is equal to p, right? That's because it's a reversible process. So now our du is equal to negative p dv, which is useful. That sort of describes our mechanical work and how the internal energy changes. Now, the sort of remaining problem we have is we don't actually know the final state of the gas yet. We know we're going to have some sort of smooth increase in pressure here. It's sort of more than the increase in pressure we'd get if we were staying on that adiabatic line. But we're going to need to use more information about this process to figure out what's going on with the pressure throughout it. In this case, because it's an ideal gas, we have a nice result over here. So we have du on the left-hand side is negative p dv, but we actually also know du by taking the derivative from our definition of internal energy. So we know that now we can use the fact that for an ideal monoatomic gas, here we have U is equal to 3/2 nRT. And, okay, now we're sort of working through the math of this here. What we have here is that U depends only on temperature. And so what's nice about this is that we can legally say here that du is equal to 3/2 nR dt. So in any process, the little change in internal energy is just related to the little change in temperature dt. From this now, we can plug that in. So now we have this expression for du. If we plug that in here, now we have 3/2 nR dt is equal to negative p dv. Okay, what was the point of doing this? Now we have an expression here that has our pressure and our temperature and our volume. And these d's here help us describe that, okay, initially I was at 400 Kelvin and 1 bar of pressure. If I do a small change in volume, maybe from 200 milliliters to 199 milliliters, so delta V is negative 1 milliliter. Let's say that that's a small enough change that pressure is constant. Now I can see exactly how much change in temperature I'm going to get. Delta V was negative 1 milliliter. I can plug that in and see what my change in temperature is because everything else here is constant. We can see from the negative sign here that I'm going to get some small plus change in temperature. And that's going to then mean I have a new pressure because I can calculate the pressure from the volume and temperature. And so I could sort of piecewise go through and see, okay, exactly how the temperature changes, then do another small delta V, see the new delta T, update the pressure, and keep going, so on and so forth. What all those little processes would add up to if I do them one after another is I would be integrating along some curve here. So the best way to do that is to, because what the variables I have are dt and dv, is that I can write p as a function of t, v, and n. So p of v, t, and n is, again, assuming an ideal gas, nRT over v. Now, when I plug that in, now I have something that I can actually integrate. 3/2 nR dt is equal to negative nRT over V dV. And again, sort of a calculus trick that we need to remember here. First thing that's nice about this is that we have some things canceling, so n and r are on both sides and those cancel. The second trick that we need to do is basically separation of variables. So to integrate this, we need to put this t over with the dt and leave the v with the dv. So if I do that, I'm going to get 3/2. And then I'm going to get dt over t is equal to negative dv over v. I'm going to move the negative over to the other side so that all my constants are on one side. So negative 3/2 dt over t is equal to dv over v. And now I'm going to actually integrate both sides from an initial to a final point. So I'm going to actually do this process here. Luckily, this is one of our integrals we've done before. Remember, dx over x, that integral is ln xf over xi. And it's actually the same integral here on both sides. So I'm going to get negative 3/2 ln tf over ti is equal to ln vf over vi. And that's basically what we need here. I know the initial temperature, I know the initial and final volumes, and then that will let me calculate the final temperature here. To do that, I'll first isolate the tf over ti. So we get ln tf over ti is negative 2/3 ln vf over vi. Then I can take e to both sides there. When I do that, I get tf over ti is equal to, okay, on this side here, because e undoes the ln, e undoes this ln, and this negative 2/3, it's going to be convenient if I want to solve this in a nice way, is to write this as e to the ln. Remember, this thing here, due to my logarithms, I can make this into an exponent. So I can make this into ln vf over vi, all of that to the negative 2/3. And now when I take, the reason we do that is because now when I do e to the ln of that, I just get my volumes there. So that's going to be equal to vf over vi to the negative 2/3. When you're going to homework problems and stuff, right, this here, you can see where that 2/3 came from is that this is negative 1 over that 3/2 from, remember, CV bar for a monoatomic ideal gas was 3/2 R. So this is negative R over CV bar is one way of writing that. Sort of an odd way of putting it, but that does actually work out to get that exponent of negative 2/3. Okay, so this then is applicable to our, so this gives us TF over TI is equal to VF over VI to the negative 2/3. And this is a monoatomic ideal gas during a reversible adiabatic expansion or compression. Okay, so this one was sort of a lot of math to go through, but it's a nice fourth type of process. We'll see that these adiabatic expansions and compressions are quite useful in designing engines and things like that, and They actually also, when we go back to the book, have a very nice simple explanation in terms of our energy level picture from exam 1. So we had to dive into the calculus to derive that, but at this point you should be able to calculate W, Q, and delta U on your own from the given information. So I'll give you a minute to do that, and then I'll show the answer below. Okay, so first, solving for TF, just plugging in, we get 484.6 Kelvin as the final temperature. Okay, Q we already decided was 0. Again, W is that integral of P dV because, again, P external is equal to P, but this is, not a very convenient way to solve for W here. A lot easier here because we know the temperatures is to first get delta U. So if we say delta U is 3/2 nR delta T, that's always true for a monatomic ideal gas, so plugging in. Then just plugging in and solving, 6.34. 2 joules is delta U, and since Q is 0, that's also equal to the mechanical work. One thing I guess we didn't solve for was the final pressure. We should do that here as well. The final state, you know that T is 484. We know that V is 0.15 liters, but to plot it on our diagram here, we can get P is nRT over V is equal to, when we do that, we get 1.615 bar. Again, comparing that to the adiabatic, to the isothermal case. In the isothermal case, we would have that 25% reduction in volume, which would increase the pressure by that same factor. So we would have 1 over 0.75, which is 1.33 bar. This is the point that's sort of on that isotherm here, keeping T as a constant 400. But since the temperature increased here up to 484.6 Kelvin, the pressure was increasing a bit faster than that. And that's our final state of the system.